Kia ora tātou. We've seen that Dijkstra's algorithm works on graphs where weights are non-negative, and in some cases it may even work when negative weights are present, but this is by luck rather than by design. In this lecture we'll look at an algorithm that is slower than Dijkstra's algorithm, but it can deal with negative weights. This is known as the Bellman-Ford algorithm. So recall that Dijkstra's algorithm builds up an optimal solution one node at a time. It builds up a set of black nodes, and once everything is black, we are guaranteed to have found the shortest paths. By contrast, Bellman-Ford solves the single source shortest paths problem by building up the optimal solution one arc at a time. So it looks for optimal paths to nodes that have a minimum weight path of length 1 arc, then 2 arcs, then 3 arcs, and so on up to n-1 arcs. We'll define the level of a node as follows. Nodes at level I have I arcs in the minimum weight path from the source. The algorithm thus solves the problem for all nodes at level 0, 1, 2, up to n-1. And notice that the longest possible path, that is a walk without repeated vertices, and a graph of order n is n-1. So let's have a look at the algorithm. So here's the algorithm. We're given a weighted digraph, G with cost matrix C. We're given a node of GS, which is the source. And how do we start? Well, we initialize this dist array by initially setting everything to be infinite, except for the distance to the source node, the dist for the source node, which we set to 0. Then we go through this nested for loop, triple nested for loop. This outer loop is just counting what level we're at, so it goes from 0 to n-1. And the inner loop chooses a node x, it chooses a node v, and it asks whether the minimum cost of a path to v and can be improved by considering the path that goes through x and then extending that path from x to v at a cost, of course, of cxv. And it just iterates through all pairs of vertices x and v. Once we've done that n times, we'll simply return the distance array. Let's look at an example to see how this works. So here's a graph, and we'll set node 4 to be the source node. And notice, well, we can process the nodes here in the algorithm in any order. Let's just stick with the order 0, 1, 2, 3, 4. So we start by initializing the distance array, and I'll write the values for dist here next to the nodes in blue rather than setting out a different array down here. So 4 is 0, and everything else is infinite. Okay, so we're up here at the top. We set I equals to 0. So we're processing our nodes in the order 0, 1, 2, 3, 4. So x is 0 and v is also 0. Can we update this infinity by considering the distance here, which is infinity, plus an arc that doesn't exist, the cost of an arc that doesn't exist. So clearly we can't make any update there. So we increment v. So v is now 1. We say, can we improve this infinity, the distance to 1, by considering the distance to 0 plus the cost of any arc from 0 to 1. Again, if we've got a value of an infinity for dist x, we're never going to make an improvement. So in fact, we can skip over looking at v equals 2 and 3 and 4 in this case, because we're clearly not going to make any updates while dist x is infinity. And so we can increment x, and again, if x is 1, we get a value of infinity here. If x is 2, we get a value of infinity. If x is 3, we get a value of infinity. So we skip all the way to the value x equals 4. So when x equals 4 and v equals 0, can we improve this infinity by considering the distance to x, which is 0, and the cost of any arc from 4 to 0. Well, there is no arc here, so we're not going to get any update here. So we'll increment v to be 1. So x is 0, v is 1. We say, can we improve the value infinity by considering the dist to x, which is 0, plus the cost of going from 4 to 1, which is 3. So 0 plus 3, which is certainly less than infinity, so we update that. Similarly, when v is 2, the distance to x, where x equals 4, is 0. The cost of going from 4 to 2 is 1. 0 plus 1 is less than infinity, so we update that. And it should be pretty clear by now that we not only do we need a finite value of dist to have any chance of making an update, but we also need an arc with a finite cost from x to v to be able to make an update. So that means instead of looping over all pairs of possible nodes, we only need to look at those pairs that are joined up by an arc. In other words, we can replace the double for loop over here through all pairs of possible nodes in G with a single for loop over all arcs of G. So let's replace this with for all x and v and eg. And notice again that the order in which I process the arcs in each iteration is essentially arbitrary. So let's roughly process them in the order of left to right and top to bottom. And well, when programming this, it would make sense to process the arcs in the order in which they occur in the adjacency list. So let's continue running through this algorithm. Let's process this arc. So we're asking, can we improve dist 3, which is currently infinity, by looking at dist 4, which is 0, plus the cost of going from 4 to 3, which is minus 2. So 0 minus 2 is minus 2, which is less than infinity. So we update that. And let's say we've got to the end of our first iteration of our for loop. So we increment to I equals 1, and now we want to go through each of the arcs again. Can we update this value by looking at this arc? 0 minus 2 is minus 2, so no update there. Can we update this value by looking at this arc? 0 plus 1 is 1, so no update there. Can we update this value by looking at this arc? 0 plus 3 is 3, no update there. Can we update this value by looking at this arc? Minus 2 plus 2 is 0, which is less than 1, so we can update this. Now let's look at this arc. Can we update this value? 0 plus 2 is less than 3, so this becomes 2. Let's look at this arc. 2 plus 1 is 3, which is greater than 0, so no update. 2 plus 0 is less than infinity, so we update that value. And 0 plus 3 is greater than 2, so no update there. So we've gone through each of the arcs again. We can update I to be 2. And again, we can process each of the arcs. 0 minus 2 is minus 2. Minus 2 plus 2, 0. 0 plus 1 is greater than 0. 0 plus 3 is greater than 2. 0 plus 2 is 2. 2 plus 1 is greater than 0. 0 plus 3 is greater than 2. And 2 plus 0 is 2. Now, we've just completed an iteration where nothing has changed. If we updated I and performed another iteration, that is, if we went through each of these arcs again, still nothing would change. We'd get the same result. So that means we can actually halt the algorithm at this point and return the result. Here's our result, which we return. So in general, what's the running time of this algorithm? All the work here is really be done in this nested for loop. When we have adjacency lists, so we can just iterate through each of the arcs easily, we need to do m work here. We need to do that n times. So we have n times m. So we get a running time of big theta m times n. Obviously, when the digraph is represented as adjacency matrices, access to the out neighbours is not so easy, and we have a running time of big theta n cubed. Okay, so how do we prove the correctness of Bellman-Ford? Well, first I'd like to point out that while we allow for negative weight arcs in these digraphs, the idea of the shortest path doesn't make sense in the presence of a negative weight cycle. And by a negative weight cycle, I mean a cycle in a digraph where the sum of the arc weights is less than 0. Let's look at an example. So the weight of this cycle is 1 plus 2 minus 5, which is negative 2. And we can see that the idea of the minimum weight path here makes no sense. So we'd expect the distance of the node from 0 to itself to be 0. But, well, let's notice that we can take a trip around the cycle and get a walk of distance 1 plus 2 minus 5, which is minus 2. So is the distance from 0 to 0 actually minus 2? Well, we could take another trip around the cycle. Minus 2, minus 1, plus 1, minus 5, so is it minus 4? And so on. In this way, that you see, every time you traverse the cycle, your cost of doing so gets lower and lower. So there's no defined minimum. And indeed, it's not just the nodes in the cycle that are affected by this. Suppose you have some other node over here, and this new node 3 is strongly connected to the cycle. So that means we can get from this node and to the cycle and back again. Then we can find a node that goes from this node up to the cycle, around the cycle as many times as we want, and then back to the node. And so we can make the weight of that walk as low as we want. And the idea of a minimum distance to or from this node doesn't make any sense. For example, we can find a walk of weight, minus 1 or minus 3 or minus 5 from 3 to 2, rather than the natural weight which we'd expect to be 1. And for that reason, we exclude digraphs that have negative weight cycles from our consideration here, and we prove the following result. Suppose that the digraph G with weight matrix C contains no negative weight cycle. Then after the ith iteration of this outer for loop, dist V is the weight of the minimum weight path for any node with level at most I. And recall that node V has level I means that the minimum weight path from the source to V requires I arcs. And also notice that since the node has at most level n-1, we show that the algorithm gives the desired result after n iterations. We'll prove this result by induction on I. So in the base case, when I equals 0, we have only the source node to worry about, as it is the only node at level 0. And there, well, the distance from the source to itself is 0, which is equal to the dist for S, which we have set here, and so the result holds. Now, we make the induction assumption that the result is true for I-1 iterations. So after I-1 iterations through this for loop, dist X is the weight of the minimum weight path for any node X at level I-1. So using this assumption, we seek to show that the result holds for one further iteration. So we'll let V be a node at level I. So V is a node where the minimum weight path from the source to V requires I arcs. And we'll consider gamma, which is a minimum weight path from S to V. Now, since there are no negative weight cycles, gamma has exactly I arcs. So we'll let gamma have this form. So gamma starts at S, goes up to Y and then on to V, so Y is the immediate predecessor of V. And we'll consider just the subpath up to Y, and we'll call that gamma 1. Now, what can we say about the subpath gamma 1? Well, it must be a minimum weight path up to Y, otherwise gamma would not be a minimum weight path. So Y must have level I minus 1. And therefore, by the inductive hypothesis, we have dist of Y is less than or equal to gamma 1. So notice that I'm using these absolute value sort of signs to represent the cost of a path. So this is the cost of gamma 1, the sum of all the costs of all the arcs in gamma 1. But now by the update formula over here, we have that dist V is less than or equal to dist Y plus the cost of going from the cost of the arc from Y to V. But by the argument we just made, dist of Y is less than or equal to the cost of the path gamma 1. So this is less than or equal to the cost of gamma 1 plus the cost of YV. But that is precisely the cost of the path gamma. So dist V is less than or equal to the cost of gamma. Conversely, since gamma is a minimum weight path, and by construction dist V is the weight of some path from S to V, we have that the cost of gamma is less than or equal to dist V. So we have that dist V is less than or equal to gamma, gamma is less than or equal to dist V, so equality must hold, and the proof is complete. So we've shown that the Bellman-Ford algorithm does indeed solve the single source shortest paths problems, so long as there is no negative weight cycle. But what can we do if we're given a digraph and we don't know whether there is or is not a negative weight cycle present? Well, let's think about how the algorithm works. Essentially, we're finding the minimum paths of length 1, 2, 3, and so on. And if there are no negative cycles, we know we have reached a solution when we've considered all paths of length up to n minus 1. And if we continue to iterate the algorithm, nothing will happen. There'll be no changes to the calculated distances. But if there is a negative weight cycle, as we continue to run it, we'll find walks of lower and lower weight. That is, if there is a negative weight cycle present, our array dist is guaranteed to change after one further iteration of the main loop in the algorithm. We can thus detect the negative weight cycle by running through all arcs a final time and watching to see if any element of dist changes. If it does, there's a negative weight cycle, and the single source shortest path problem has no defined solution for this digraph. If there is no change to dist, the values calculated in dist are indeed valid, and they are the solution to the single source shortest paths problem.